All right, so welcome to another edition of Mechatronics. We are going to move right along into element interconnection laws. Ooh, should I take the entire video with just my forehead missing?
I think you should just want camera to belly button.
I feel self-conscious. My face is my best feature. All right, so we're going to talk about element interconnection laws, which is note set 31. If I can find them, that would be great. All right, so we're going to write these laws that are analogous to Kirchhoff's two laws, voltage law and current law. So the first one is called the Compatibility Law. And afterwards I want you to tell me, it already says it in your notes, which one it's analogous to. Alright, so I'm going to draw this in purple, because I wore a purple shirt today, just feeling, I split open my other purple shirt, but I'm going to, it was because my arms were so big, that's why. It was the elbow that split out. At least that's what I'm telling people. Alright. So the compatibility law states that the sum of the across variable drops on branches around any closed loop pretty obviously on a linear graph, because that's what we're all about right now, is identically zero. I'm just going to say is zero. Hope you guys are tracking with that. Or, if we were to write this as an equation, it would be that the sum from I equals 1, that's going to be on the internet forever, dude. Of the generalized across variable drops. Oh man, that just never is going to go away. Yeah. Skoosh. All right. For any n elements, oh man, I should have tried to get him on video as he walked by too. Forming a closed loop on the graph. So, which of Kirchhoff's laws is a subset of this law? Voltage law. So loops can be inner loops or outer loops. So I'm going to draw 3 loops. Okay? There's a loop. There's a loop. And where's the last loop? This is one of those things. Yeah, you guys know those, like, how many triangles are in this diagram? It's like that. But it's loops. And yes, it was worth mocking. All right. An example. For the linear graph shown, what is the compatibility equation? All right, yeah, so Vs minus Vr minus Vc equals 0. Boom. So this is something that, this is a linear graph of a circuit, right? So like we're really familiar with writing this equation, but we could do this with any linear graph. So we can include mechanical systems. Soon we'll be doing electromechanical systems. That'll be fun. Oh yeah, lab this week's going to be great. Oh, I'm so excited. But there's still a lot of things that need to come together still for it to work, so I really hope it works, because it's going to be fun. That was just my mind just going somewhere else for a second. I hope that's okay. Doesn't really matter if it's not. So, for mechanical systems, the compatibility equation is a geometric constraint that ensures the connected elements remain so. So, it's like, oh yeah, this spring is connected to this mass, and that requirement, so if that is no longer the case in the physical system, then that compatibility equation will not hold. But assuming that it is connected, then the compatibility equation should hold. For electrical systems, it's Kirchhoff's voltage law. Okay, continuity. Purple again, those of you keeping score at home. The sum of through variables What are through variables? Give me a couple examples. Great. What's the last one we talked about? For rotational systems. Torque. Yeah. Sum of through variables flowing into any closed contour I'm going to explain what that means in a second. In a linear graph, is 0. That is I'm going to inline equation this one. So sum from I equals 1 to n of, here comes generalized through variable, so sum up all of the through variables, set them equal to 0 for purple again, for any n branches that intersect the contour. So I didn't mention anything about nodes. Is that bothering anyone else? Yeah. So when we did Kirchhoff's current law, we talked about nodes in the circuits, right? But we didn't talk about nodes here, so this is a subtle difference, but it actually still includes Kirchhoff's current law as a subset of it. So we can essentially make our nodes bigger than we used to, okay? So let's see what that means. So let's say that you've got some branches coming into a node. So you can draw a contour around a node. A contour is a line that you draw that comes back to it. If it's closed contour, it's a line that you can draw that comes back to itself. Okay, a curve. Draw that comes back to itself. So this is a closed contour. And we could draw it around a node, and then we just have essentially the node concept that we did before. So if we just choose this node, we draw a contour around it, then we say, oh, okay, the through variable, so let's say it's current. I1 minus I2 plus I3 is equal to 0, right? So I'll do it with generalized through variables. F1 minus F2 plus F3, that's a really big F, F3 equals 0. But we don't have to limit ourselves to drawing contour around a node. We could draw a contour around any number of branches and nodes. So let's draw this contour. Woo. Yeah. And this is another closed contour. So now our continuity equation that's associated with this is going to ignore all of this stuff going on inside of it. It's just going to say, okay, if we sum up all of the through variables that cut through this contour, that go into it or positive, out of it or negative, that should equal 0 as well. So it's going to be negative F1 plus or minus F2. Plus F2, good. Plus or minus F3. Minus F3 equals 0. Great. For mechanical systems, the continuity equation is an expression of Newton's second law for a massless point. Okay? Massless point. Sum of the forces is equal to MA, but if M is 0, then the sum of the forces is equal to 0. So when we use the continuity equations for a mechanical system, we're just saying, okay, here's a massless point. For electronic systems, it's Kirchhoff's current law. Okay, series and parallel connections. We mention these because they're special cases that we see a lot, right? So it's nice to just be able to say, oh, here are a bunch of branches in series. If we were to draw these two contours, then we would find out that F1 equals F2 equals negative F3, right? Does that make sense? We could do. Was that too many steps skipped? Okay, I'm gonna back that up. Okay, here's the first one. F1 is going in minus F2 going out equals 0. Therefore, F1 equals F2, right? This one says F2 plus F3 equals 0. So F2 equals negative F3. Yeah. I mean, if we draw them all in the same direction, which we typically would, then it would just say F1 equals F2 equals F3. I just put the one drawn in the other direction just to make sure that we're staying honest with our stuff. All right, here's a parallel connection. This one happens quite a bit too. So we have, well, let's draw. So these were the continuity equations. Let's draw the compatibility equations here. So if we were to go around a loop like this inner loop and this inner loop, these two loops, then the first one would say V1, I mean, I guess I drew that arrow this way, so I should say negative V1, right? Negative V1 plus V2 equals 0, which says V1 equals V2, right? And the other one is that negative V2 minus V3 equals 0, which says that V2 equals negative V3. Life of Padre. I don't know what this is. Yes, sorry?
He's a folk singer-songwriter in Seattle. You'd like him.
That sounds cool. Yeah. Out of touch. Getting old. It's pretty sad. All right. So that's how we come up with laws of interconnection. So we've got, as you may recall, elemental equations defined for A-type, T-type, D-type elements, right? And then we also now have element interconnection laws defined. So given our path that we took previously, we're getting pretty close to solving actual problems, I think, right?